Good evening and welcome to the Exploratorium and to Everything Matters, Tales from the Periodic Table. Tonight we are doing sodium. And for our talk now, I want to introduce you to John Largier. And he's a professor of coastal oceanography at the University of California, Davis. He's also a science in residence here at the Exploratorium, and he helps us understand salinity of the bay and how that changes and how that works, actually. His research, teaching, and public service are motivated by contemporary environmental issues and centered on the role of transport of plankton, larvae, contaminants, pathogens, heat, salt, nutrients, dissolved oxygen, and sediment in the ocean, in the bay, near shore, and in estuarine waters. So I'd like to now introduce John Largier. He's going to talk about all of that.
Thanks, Ron. Well, thanks, Ron. I'm going to talk about why the sea is salty and who cares. That's one little part of the sodium. Sodium is salt, sodium chloride. And really the gist of the story is that ocean water is more dense, and that's what pushes it into the bay. So we'll go from a little bit of chemistry across to physics and eventually to ecology. If you look at seawater, you've got a big box of water, turquoise with a little bit of salt in it, a little bit of dissolved solids. Of those dissolved solids, you get the green, which is chloride ions, and the orange, which is sodium ions. There's magnesium and sulfate and other things. But sodium and chloride are the key elements. And why is that? Well, or where do they come from is one of the things. The sodium comes from weathering of rocks, the rivers flowing into the ocean, and the chloride comes more from volcanic and hydrothermal vents, etc. But both of them, the key point is that once they get into the ocean, they stay in the ocean. So they're not eaten by anything, they're not reacting, they're not precipitating, they just stay there and slowly accumulate. As opposed to a lot of the other substances that might weather out of rocks and come into the ocean, it gets processed. So at the bottom I have this 100 million years. What do we mean by that? Well, basically those substances are conservative. They're not being, as I say, processed, they're conserved, and probably a sodium ion is spending 100 million years from the time it came into the ocean through weathering the rocks, and maybe it lands up in a salt marsh and precipitates out into an evaporative deposit. That's about the only way sodium gets out of the ocean. So it's pretty much there forever. And in actual fact, we treat it as a constant. Ocean salinity is 35, which means 3.5% salt, and that doesn't change. And it's pretty much the same everywhere, but not quite. So if you looked at the surface of the ocean, you can see some colors there. Hopefully you can recognize them, the Americas and Africa and so on. Average is 35, and salinity. So in actual fact, we started off calling salinity 35 parts per thousand, in other words, 3.5%, but now it's defined by conductivity. So Laurie had a little conductivity meter out here. How much electricity is conducted by the water is actually the definition of salinity. So we don't even call it parts per thousand anymore. We just say it's 35. It's a ratio. But kind of means that there are 35 grams of salts in a kilogram of water, of which that you can see about 11 grams of sodium and about 19 grams of chloride. I think magnesium is next. It's 2 grams, and then, or sulfate is 2 grams, and magnesium is 1 gram. But those are really the dominant ones. So on average it's 35, but of California it's about 33 out in the Pacific Ocean. So you can look at the colors. The green in the Pacific is maybe 35, but as you get closer to California, the water we're getting off San Francisco here is more like 33, and then that which upwells the really cold water is 34. So these are tiny changes by any measure, but they're really important in the ocean. And why are they important? Well, physically, the reason why they're important is because salty water is denser water, which is curious because Ron was saying that sodium is actually lighter than water, but when you dissolve it in the water, you kind of can squeeze some more mass into every little bit of volume. So water that has salt dissolved in it, sodium and chloride, is actually heavier. Water weighs a ton. A cubic meter of water weighs a metric ton, but salt water is heavier. So instead of being 1,000 kilograms per cubic meter, it's 1,025. Small difference, 2.5%. But again, it makes all the difference. On the diagram here, it's actually given in grams per cubic meter. So 1 gram per cubic meter is the same as 1,000 kilograms per 1 gram per cubic centimeter is the same as 1,000 grams per kilograms per cubic meter. Getting confused. But the main point being the x-axis is salinity and the y-axis is temperature, and the lines are equal density. So I'm going to have to stand off the stage all the time here, because if you go across from low salinity to high salinity, you're crossing lines of equal density. But if you go from warm water to cold water, you're also crossing lines of equal density. The colder the water is and the saltier the water is, the denser it is. The denser it is, basically the heavier it is. And this is where the physics comes into it. There are other cool things about salt, and Ron talked about the freezing point. The water freezes at a lower temperature when it's salty. But the other thing that happens after about 25 parts per thousand is that you don't get the maximum density occurring before freezing. So you know that in fresh water, when water gets down to 4 degrees Celsius, it's the densest water, sinks to the bottom of the lake. And the colder water, 0 degrees, is on the top of the lake and freezes. So you get nice ice in a lake. In the ocean, it doesn't happen like that. 4 degrees, 3 degrees, it carries on getting denser, denser, denser. So dense water at 0 degrees falls to the bottom of the ocean, and you struggle to make sea ice in the same way as you make freshwater ice. So there are a lot of other aspects of dissolved salts, in particular sodium, in the ocean. But the main thing I'm going to talk about is density. So seawater is heavier. If you have a pile of seawater on top of you, it'll weigh down on you more than a pile of fresh water. So here we come to the bay. How does seawater get into the bay? There are basically two ways. The one is, you know that the tide in the ocean goes up and down, 1 meter or 2, and as it's going up, the water level in the ocean is higher than in the bay. If you were down sitting on the bottom of the bay at a given level, and there's more water on top of you, you would feel more pressure on you than if that's in the ocean, and then somebody else is in the bay at the same time with less water. You feel less pressure, creates a pressure gradient, which creates a force. So you get back to old Newton, and force equals mass times acceleration. So if the water level goes up in the ocean, it basically is a force pushing water into the bay. So that's what I have here. Tide changes water level high in the ocean. The weight of more water in the ocean will push water into the bay. But you know that the tide then goes down, and 6 hours later, it goes the other way. So the water goes in, and as soon as it comes in, it goes out. And the other thing that happens is that the water in the ocean, even if it's the same level, but underneath the salty water, you're getting weighed down on, there's more pressure than if you're in fresh water. Same amount of water, but it's lighter. It doesn't weigh down on you so much. So the pressure gradient from ocean to bay is there. It's weaker, but it's persistent. So that small density difference does not give you such a strong pressure gradient, but it keeps there. It's all the time. It doesn't change much with the tide. So density of ocean water is the second way that the water gets into the bay. The weight of the ocean water is more. So again, you have a pressure gradient, force equals mass times acceleration, and water moves into the bay. And as the tide goes to and fro and to and fro and to and fro, this density gradient is always pushing that dense water in at the bottom. And in the end, over time, if you average over a week or days, you learn that's what really gets the water into the bay. So I have a couple of little movies here, which I'll show you, and we can look back at this in a moment. But these, or maybe I'll just talk about this briefly. The yellow water here is dense water, so it's like seawater, and there's clear water in a tank, which is like fresh water. And you start off with dense water one side and fresh water the other side. And you take the wall out between them, and the dense water pushes in underneath. Just like if you started off with seawater on one side of Golden Gate Bridge and fresh water the other side, and you lifted the wall up, that dam they wanted to build back in the 60s, and you'd find this sort of process going on. It's called a lock exchange experiment. It's one of the favorite experiments in fluid dynamics. So we were doing this for a class up at Bodega Marine Lab. Green water on the right, and fresh water on the left. Pull the wall out of the way, and of course that dense water, there's more pressure underneath it. It pushes the water across, and it intrudes across the bottom of the tank. We don't have a whole ocean, so it's running out of green water, but you can get the idea of that salinity intrusion that goes into San Francisco Bay every tidal cycle. But it actually keeps pushing more persistently. So it comes in with the tide, goes back a little bit, comes in more, and You see a lot of interesting other wave effects here of it running up the beach, just like a wave runs up the beach and reflecting and so on. You can also do this, as we're doing now, in computer models, where the dark blue again is seawater and the light blue is freshwater. All of these are a little different because of the density difference. That previous laboratory model was not really seawater, it was sugar water, and it was not really 2.5% density difference, more like about 7, I think it was about 7% density difference. In that shallow water, you need a little more force to get them to exchange. In this case, it's about 20 parts per thousand salinity difference, the equivalent. So it's more like seawater done in a computer model, and going a little slowly here, but you can see the dense water pushing in underneath, and as it does that, you see little roll-ups and little instabilities developing. You can also see the fresh water pushing out on top. So this would be the water going out of Golden Gate out into the ocean as a plume, and that would be the salinity water going in. And you can see that the two mix together, and that creates a whole lot of other interesting stories. But the basic idea, the density creates pressure gradients that push the seawater into the bay. It would not get in nearly as effectively if the tide just went backwards and forwards and backwards and forwards. And the next one is very similar, slightly different color scheme. The density difference is a little bit smaller, and the main thing you see in that case is that there's more mixing. Pushed the wrong, did something. Here we go. So you can see there's a little less density difference, and the fluids mix up a little bit more. So does this happen in San Francisco Bay? Sure it does. Here's some data from 1997, January 28th. Why did I choose this? Because it's a nice picture and we had it plotted. On the top is our observations, on the bottom is a model. The dashed line is Golden Gate, and what you're looking at is a section with this being the surface and that being the bottom. There's Golden Gate. This is coming up to Rio Vista in the delta. Here's Carquinez Bridge. On the left side of that is South Bay, going right down to Dumbarton Bridge, San Mateo Bridge, Dumbarton Bridge, down towards San Jose. And on the right-hand side, you see it better. The red here is 28 parts per thousand. This red line is 2 parts per thousand, basically fresh water. And you can see that fresh water on top and the salt water underneath. And then proving that you can do it in a computer model, you can share the same process. So there's your salinity wedge, or your salinity intrusion, or your salt wedge, which is coming into the bay. It changes, of course, and so here's the model showing different freshwater flow rates. The freshwater is interesting because while you might push the salt water back with the freshwater, at the same time you're increasing that density difference, which allows the salt water to get in. So you might spot over here the flow rates coming out of the delta of 55, 260, 630, 2,810, a whole lot more flow. It doesn't push the salt water out of the bay. It's like pushing against a spring. And you get more and more of this salt wedge-like structure. Whereas at the top here, it's more of a tidal structure, just mixing water to and from the bay. So you're seeing the difference here at the top between the tidal mixing. It's like you have seawater one side and fresh water the other. Imagine there's no density difference. You took a teaspoon and you just mixed it. That's what the tide does, and it'll kind of mix things out. Whereas the density difference, you put the two together and you'll get that lock exchange interleaving process going on. And that's what pushes the water into the bay. Spent a lot of energy, a lot of fresh water is allowed to go into the bay to keep that salt water back. We don't really want to suck salt water into the pumps and send it down to Southern California. So you keep pushing the salt water back with fresh water. And you can see particularly here, the measurement you use is X2, the distance of the 2 parts per thousand from the ocean. This is the bottom graph. This is about 25 years of data. 40 kilometers, you can see on the left-hand side, 60, 80, 100 kilometers right into the delta. 75 is the beginning of the delta. And you can see the X2, that this 2 parts per thousand salinity intrudes into the delta at different times. Most noticeably here in the 1970s during the drought, here in the 1990s during the drought, and if this paper was written in 2002, so we don't have recent data, you'd see another intrusion. And how do you stop salt water going to the pumps? Well, you have to keep fresh water flowing into the bay. So not only is fresh water important for ecosystem of this delta, but it's important for the water supply as well. So, and the top graph there then is the delta flow. How, when it goes up, it pushes the X2 back into, sometimes beyond Carquinez, down to 50 kilometers is about Carquinez Strait. So sodium, suddenly we've moved from some chemistry to the water density, to the circulation in the bay. How does the water move in and out? Difficult to envisage, but probably the best way to envisage the salt wedge is to look at the fog. It's the same thing, really. Trying to find some good pictures of fog is really difficult, because when you try and take a picture of fog, it's foggy, and you cannot see it so well, so you have to sort of be in the airplane at the right time. So I struggled to find them, but this one gives a pretty good idea of the fog is high up at the top of Golden Gate Bridge, and it forms a wedge just like that salt water reaching in towards Berkeley and Oakland and thinning out. It's a fog wedge, and that's really what that salt wedge looks like going into the bay. Here you can see it backing up behind Mount Tam and the ridge north of the bay, just like the salt water backs up behind the tidal bar offshore of San Francisco Bay. And here you can see a picture from Sausalito looking across this wedge, and you can see the wedge shape. Same story, that cold air is dense air, and so it's trying to push in underneath the warm air of the bay, and it's nicely marked by being foggy. It's a little more complex because the fog can kind of vaporize and all the thermodynamics, whereas the water comes into the bay, can't vaporize, it has to kind of get out of the bay again. So that's sort of the physics, and what the contemporary issues are that we're looking at is that deep, cold, salty water is also very enriched. So you probably all know that the water is cold along the California coast because of upwelling. So the north winds that we have, they pull up water from maybe 1,000 feet to 300 meters, and the water down in the ocean is down dark below the photosynthesis, and it's rich in nutrients, it's low in oxygen, it's rich in carbon dioxide, which makes it low in pH. It's basically water from the compost heap, which is great because it makes things grow, but that low oxygen can be a problem. So we have that salty cold water getting into the bay is interesting and very useful, and it's great because it brings in lots of nutrients which enrich the bay, but as we may be enriching the bay too much with a lot of wastewater, suddenly people are saying, well, the ocean's polluting the bay. So we need to figure out how much the ocean is nutrifying the bay and how much the wastewater is nutrifying the bay. So it's become quite an issue. The water that's not as cold is not as nutrient rich. Same thing with oxygen. The water that's cold can be low in oxygen. In the last decade or so, it seems to have got lower. So maybe we're digging deeper down in the ocean, or maybe the oxygen in the ocean is getting lower. These are probably all associated with climate change. And here in 2011, April 2011, March 2011, the USGS goes out once a month and does a survey. That's the last time we had good river flow. And this is again a section only looking at South Bay, but you can see this pink, which is oxygen levels below 80% of saturation, getting down to values which are concern to wildlife. And you can see this wedge of pink water, which is a wedge of salty water and a wedge of cold water stretching into South Bay. So we've been studying this, but there's not been much fresh water, so not much stratification, and it hasn't happened the last few years. But we're talking about oxygen levels which are low enough to be considered a pollutant by the Regional Water Quality Control Board. If it were due to pollution, it would be a problem, but it's perhaps a natural process, but perhaps something that's been aggravated by climate change. And then pH, or carbon dioxide in itself, is not the issue, but pH is ocean acidification. So it's ocean acidification coming into the bay. So that's where we're going with things. Had a nice little article recently in Bay Nature, which I probably should have put into the presentation, so you can read what lurks beneath about some of the work that we're doing. And really what we're trying to understand is the reach of the ocean, not where does the salt water go. Remember, salt is conservative, but where do those reactive things go, the oxygen, the nutrients, the pH? And it really depends on how old the water is. So when there's a strong freshwater flow, the salt might not go very fast, but it gets there very fast. And so probably the reach of the ocean in a reactive ecological way is more when there's fresh water. So that's just a little story going beyond sodium as an element into sodium chloride as a salt, into the density of ocean water, into why does ocean water move into the bay, and some of the critical ecological issues. And I end there with just a piece of art which is actually data that being collected at the Exploratorium and at Bodega Marine Lab, tracking levels in oxygen and carbon dioxide and salinity. This is in 2014, and you can see it bumping up and down as every time it upwells in the ocean, you get some more of this low oxygen, cold water coming into the bay or not, and that's the question. So thank you very much.